Hi there, in this video I want to cover the accuracy of the OWON XDM1041. The previous video covered the hardware and the user interface. If you recall, I was quite impressed by the hardware and build quality, not so much about the firmware, which is revision 1.2 in my meter, but more about that later. Originally I planned covering the SCPI interface and showing a little utility that uses it, but investigating the weirdness of the temperature measurement took a lot longer than planned, so I have to move that to the next and hopefully last installment. A lot in this video is about accuracy, and this involves taking many hundreds of measurements with the XDM1041 and comparing them to my references or reference meters, which in most cases is the Agilent 3441A and occasionally the BM869S. Since all these meters, as well as my DPS 5005 base power supply and the FY6000 function generator support remote control and recording, I automated most of these tests and did not hang around while they were running because it's really boring. All I'm going to show are the results. But we start with some manual action of stuff that isn't in the spec sheet of the XDM1041. First up, burden voltage. You do want to know a meter's resistance in current mode, and the lower the better, because that determines how many volts or millivolts are dropped by the meter when measuring current. For 5 amps, it's almost too low to measure with a BM235, 0.1 ohm or a loss of 0.1 volts per amp. Same for 10 amps. For 500 milliamps, it's about 1.3 ohms, or a loss of 1.3 millivolt per milliamp. Same for the 50 milliamp range. For 5 milliamps, it's 101.2 ohms or a loss of 0.1 millivolt per microamp. And the same for the 500 microamp range. These values are about the same as many other meters, and I repeated the test in AC current mode with the same results. The input resistance in the DC volt mode was 10 megohm in all ranges, and a repeat test for AC volts showed the same. You want this to be high to minimize the influence of the meter on the circuit you measure. 10 megohm is the usual resistance you would expect. In this test I want to see the XDM1041's behavior with a signal that is mixed AC and DC. The red BM869S shows what to expect, which is absolutely fine. But this test was easy, because AC and DC parts were very close. Auto-ranging in many meters fail when measuring a mixed AC and DC signal with very different magnitudes. Let's see what the XDM1041 does with this high AC signal when I start adding a DC component. You can see that the DC voltage shown on the XDM1041 is not correct. It falls more and more behind. The AC part is correct, but the DC part is wrong. Instead of minus 10.2 volts, it shows only minus 3.7. But if I select manual range, it shows close to minus 9 volts. That is still not very exact, but at least a lot closer. The conclusion is that with many other meters, the XDM1041 struggles with mixed AC-DC signals, and at the very least you should turn off auto-ranging when you suspect such a mixed signal could be present. Let's move on from weird mixed inputs to nice and well-defined inputs and see how the XDM1041 deals with those. The specs of the XDM1041 are in the user manual that you see here, and that can be downloaded from OWON. It's actually quite a reasonable manual, much better than the machine translated things you get sometimes. The specs are close to the end. Note that they are only valid for low mode. Why is that? I think the reason can be seen here. This graph shows the XDM1041 measuring a constant reference voltage of 4.09583 volts over 1800 seconds. Cycling the speed setting from high to low to medium and then back to high. The difference appears fairly dramatic, but we are really low in the weeds here. As you can see, the error percentages are quite small, even for high, but still it's obvious that high speed comes at a price of a lot of noise and reduced accuracy. If I had to guess, I think high uses one of the faster ADCs of the HY3131, which has only 19 bits compared to the slower one that has 24 bits resolution. Also, low obviously does some averaging and is less noisy than mid. I should also say that this graph, as well as all my accuracy measurements coming up, were taken from the SCPI interface, which can show the values at a higher rate and with a lot higher resolution than the rounded number shown on the relatively slow updated display. The normal display hides a lot of the noisiness from the user at the cost of reduced resolution. Let's start with DC volts. As you can see, from 50 millivolts to 500 volts, we should expect an impressive 0.05%, but then there is the 5-digit part. What does that mean? I explain it here for the DC volts, but it's similar for other functions. For example, consider measuring a true value of 10 millivolts in the 50 millivolt range. From the spec we expect 0.1% accuracy, meaning the meter could show anything from 9.99 to 10.01 millivolts. But then we need to consider the digit number, which is 10 in this range. This may add or subtract to the displayed value, which means the in-spec range is actually 9.98 to 10.02 millivolts, or in fact 0.2% accuracy. The effect of the digit part is not constant. It is more for smaller displayed values than for larger, and worse for smaller numbers in general. This is shown in the graph here. The blue line is the basic accuracy in accordance with the spec. The red graph is the actual accuracy that would still be in spec if you included the digits number. Our example of 10 millivolt increasing from 0.1 basic accuracy to 0.2 still in spec accuracy is right here. The reason I show the red graph from 500 to 1000 volts as dashed is because there's probably an error in the spec for that. This footnote number 3 says we need to add an additional error of 0.02 millivolt for each volt over 500 volts DC. That can't be right. For 1000 volts, that would be 500 times 0.02 millivolt or 10 millivolts. That is so little it can't even be displayed in that range. I think what they wanted to say is 0.0 volts, not millivolts, which means at 1000 volts we have an additional 10 volt error, which sounds much more likely, and it means from 500 to 1000 volt the accuracy drops to just about 1%, shown by the dotted line. This doesn't mean a specific XDM1041 meter is as bad as the red line implies, only that it could be, and we would have no reason to complain, as anything on or below the red line is in spec. But usually meters are much better than their specs. And this bears out in this case too. The DC volts error against the adjuvant in the very important range from 500 millivolts to 50 volts is just around 0.01%, which is much better than the 0.05% basic accuracy from the spec. That continues with an error around 0.02% from 50 to 550 volts DC. The millivolt graph covers a lot of ground, so I used the logarithmic scale for the x-axis and I marked the different ranges. As expected, the error increases the closer you get to the beginning of a range. The XDM1041 just exceeds the promised 0.05% base accuracy at the very beginning of the 500 millivolt range, but not if you consider the digit number as well. In the 50 millivolt range, it stays with 0.1% down to 20 millivolts. The increasing error for lower voltages is partly the effect of the digits as explained before, and partly the effect that in general percentage error increase the smaller the value. 1 millivolt error at 10 millivolts is 10% error, but the same 1 millivolt at 100 millivolts is only 1%. Overall, I'm quite happy with the XDM1041 DC volts accuracy. It's generally considerably better than its spec, and it justifies its 55,000 count rating. DC current now, and again the XDM1041 is way better than its specification. As comparison for higher currents, I use the BM869S because the adjuvant is limited to 3 amps and I generally stop at 2.5 amps. Naturally, in the amps mode, the error percentage increases with very low currents, but from 0.5% onwards, it's less than 0.04%, a lot better than the promised 0.15%, and it improves further to 0.02% for 1 amp and higher. The milliamp mode uses again a logarithmic scale because it covers even more ground than the millivolts. Overall, currents larger than 1 milliamp have an error of less than 0.02%, but even down to 10 microamps, the error is less than 0.1%, a very good result. AC volts is generally less accurate on most multimeters, and the XDM1041 is no exception. It is also not the easiest thing to measure, especially millivolts, where induced noise from nearby power supplies and LED lamp drivers becomes significant. I should work out a better shielded setup for the AC millivolts, but for now I think it's fair to say that the AC volts accuracy is better than 0.2%, at least for 0.5 to 260 volts, which is the highest stable sinusoidal AC I can produce right now. That's still better than the spec. As with many multimeters, AC needs a certain minimum signal level to be measured reliable, which is explained in that note number 4 of the spec sheet. The XDM1041 needs at least 5% of the range for the stated accuracy and degrades if measuring signal levels that amount only to 1 to 5% of the range. This is a common limitation, and it's good that it's stated and not glossed over as other brands do with their AC accuracy specs. The same limitation is stated for AC current. For testing, I used the BM869S as comparison because the 3441A has only a very limited AC current measurement capability. The big caveat is that the BM869S AC current accuracy is also just 0.5%, so while I found that the two meters agree within 0.2% in the range from 0.5 to 6 amps and 0.15% in the range from 5 to 500 milliamps, it is impossible to say which one is the more accurate meter. The only takeaway is that the XDM1041 stays reasonably close to the BM869S, so it's likely that both exceed or at least meet their stated accuracy. For resistance, I tested the XDM1041 against the collection of reference resistors I have. All are at least 0.1% accurate. Some, as these two, are actually 0.01%, and this 10K resistor is 0.005%. As the note number 7 states, I used rel, but of course this makes only a difference at very low ohms values. The XDM1041 meets or exceeds the expected accuracy of 0.15% without problems, the exception being the 10 megohm resistor, which is slightly outside the 0.15%, but for that range the spec is actually 0.3%. Of course, you have to keep in mind that the tolerances of the reference resistors could add or subtract to the tolerance of the meter, but for example, here we have a cluster of 3 different 10K resistors with 0.1%, 0.01% and 0.005% accuracy, and they all sit really close together. So it's clear that the only error here is basically that of the meter, which is very low indeed. If you have seen the last video, the function the XDM1041 has the most trouble with is capacitance, and verifying capacitance accuracy is tricky too. Good reference capacitors with low tolerances are expensive, difficult to get, and generally only available for low capacitance values. My selection are these mica capacitors of 1 nanofarad with 1% tolerance. This 10 nanofarad cap here also has 1%, and the 20 nanofarad next to it is 2.5%. The ones in this box go from 100 nanofarad to 2 microfarad and all have 5% tolerance. And finally my box of electrolytic caps, all Nichicon branded, with 20% tolerance. To get around the high tolerances for the larger caps, I use a reference value established with a dedicated LCR meter, which has 2% accuracy for the larger electrolytic caps, but is otherwise 1% or even 0.5% accurate. As with resistance, the tolerance of the meter could add or subtract to the tolerance of the capacitor, or the value measured by the LCR meter and its tolerance, so it's quite difficult to give a clear verdict. If we take the reference capacitance as true, then the XDM1041 is certainly within its spec, except for the 100 microfarad value, which is a bit outside. The node number 9, which OWON added to the capacitance spec, is a bit strange. My meter basically stops at 1 nanofarad, so lead capacitance, which is generally in the picofarad range, never shows, and there is no point to use rel. The other interesting bit is that the accuracy is only from 5% of range onwards. That means the lowest value measurable with 2.5% is actually 2.5 nanofarad, not even 1 nanofarad. The thing about the use of non-film capacitors causing extra and unspecified errors is rather cheeky. While film capacitors are common, that statement excludes a lot of other types. Is this supposed to mean that all bets are off if you dare to measure mica, paper, ceramic, tantalum or electrolytic capacitors? That's a very poor show, OWON. Capacitance is certainly the weakest function of the XDM1041, and if capacitance mode is important to you, and if this meter is your only method of measure capacitance, you better look elsewhere. That said, except for extremely low or high capacitance values, the function works for all types of caps despite node 9 and with reasonable accuracy, but in some cases you have to use manual range. I measured the 3 dB bandwidth as 8 kHz using a 1 volt RMS sine wave as input signal. To its credit, the bandwidth is wider than the spec says, but 8 kHz is still too low for most audio applications. On the other hand, frequency measurement with the XDM1041 works pretty well. In this test against my GPSDO, the error was less than 0.0023% for the whole range from 1000 Hz to 64 MHz, which is very good. The test used a constant 1.6 volt RMS, which is what my GPSDO delivers. This is more than what the node number 8 state is needed for frequencies less than 10 MHz, but just about half of what is needed for frequency higher than 10 MHz. Yet the XDM1041 had no difficulties and went even slightly further than the stated maximum of 60 MHz. Finally, temperature, which is a strange one for the XDM1041. If you recall from the previous video, the XDM1041 offers two modes. One is KITS 90, really meaning K-type thermocouple using the International Temperature Scale, or ITS, of 1990, and PT100, which uses the temperature coefficient of a platinum-based resistor. K-types are far more common and versatile as multimeter temperature probes, and it's interesting to examine the XDM1041's implementation because there are some quirks. For this, it's necessary to understand how K-type thermocouples actually work. Thermocouples consist of a connection of two dissimilar metals. In case of the most popular K-type, it consists of two alloys called chromel and alumel. Whenever two dissimilar metals are in contact, a voltage is generated depending on the temperature of the junction. I won't go into why in this video. To use this effect for measuring, we need to connect these chromel and alumel wires to copper-based circuitry in our multimeter, and this inevitably causes another 2 points where dissimilar metals meet. So we have a chromel copper connection producing a temperature depending voltage and another alumel copper connection that does the same. Luckily, the copper parts cancel out and we are left with a voltage which is exactly the same as a second chromel alumel junction but opposite in direction. This remains true even if there are more metal-to-metal junctions, like the sockets that have a nickel surface coating on a brass body and so on, which are then soldered to copper PCB traces. The important part is that all the extra junctions are symmetrical on both sides of the chromel and alumel path. If that condition is fulfilled, we can simplify our consideration to just the two junctions where the chromel and alumel wires meet. The first is obviously the sensor itself. The second junction is usually referred to as cold junction because it is usually colder than what you stick the other end of the probe in, but it doesn't need to be if you measure frozen stuff, for example. For each thermocouple type, the American National Institute of Standards and Technology, or NIST, has compiled tables and complicated formulas that give the voltage of a thermocouple depending on temperature and the reverse function to get temperature that causes a certain voltage. The reference junction for these tables is defined to be exactly at 0 degrees Celsius of an ice bath. Since it's unlikely that you want to climb with your multimeter into an ice bath every time you want to measure temperature, all multimeters providing the temperature measurement function using thermocouples have a second temperature sensor inside that measures the meter's ambient temperature, which is assumed to be the cold junction temperature, and use that to compensate for the absence of ice baths. For example, assume the meter is at 20 degrees Celsius or room temperature, but the sensor end is slightly hotter at 25 degrees Celsius. If you look up 25 degrees on the NIST tables for K-types, it says that it will cause a voltage of 1 millivolt, shown here as Vsense. If the meter were at 0 degrees Celsius, that voltage would also appear at the cold junction, but it's at 20 degrees Celsius. The processor measures this 20 degrees Celsius and calculates or uses a reverse lookup to find the equivalent voltage for K-type sensors at 20 degrees Celsius, which happens to be 0.798 millivolts. It stores that value as its cold junction reference. When the processor now measures the voltage from the K-type sensor, it sees only 0.202 millivolts. It now simply adds the cold junction reference voltage of 0.798 millivolts and gets back the 1 millivolt. It then calculates or looks up the equivalent temperature for 1 millivolt and gets 25 degrees Celsius, which it displays. Because of the way this works, you can always get the cold junction temperature, which should be close to ambient room temperature even without any K-type sensor. All you have to do is to provide 0 volts to the sockets, for example by shortening the leads or leave them open. This means the processor adds 0 millivolts to the cold junction reference voltage, looks that up and displays it, which is of course exactly the cold junction temperature. All this works the same for any meter with K-type probes. Now for the XDM1041 specifics. In the XDM1041, the temperature sensor is actually inside the HY3131 chip, so right in the middle of the multimeter and quite a bit away from the sockets where the K-type is plugged in, which would of course be the best place for sensing the cold junction temperature. The position of the sensor so far away from the cold junction makes the measurement accuracy depending on how close the cold junction and internal temperatures really are, which raises the question of heat sources inside the meter because it does get moderately warm inside during operation. Of course, we know from the first video that the XDM1041 is never really off, only on standby. The HY3131 chip uses very little power, and I did not detect any warming of the chip itself during operation. The same is true for the processor, which is on the PCB below. I think a lot of the 3 watts the meter consumes during operation goes into the LCD backlight, and on the lower PCB around here there is some resistor that gets pretty hot at 100% backlight intensity, which is the default. Running the backlight at lower intensity reduces the internal temperature by 2 degrees in my unit. With these details out of the way, the XDM1041 temperature measurement mystery started when I wanted to see how the XDM1041 warmed up from being off. I shortened the leads and recorded the cold junction temperature. To my surprise, it was a very distinct staircase, not a smooth curve. The steps occur exactly every 600 seconds, which is every 10 minutes. This continued on the right even after the meter had been on for quite some time. Because the steps are lower, the scale is larger and it shows the noise as well as the overshoots enlarged. During some real temperature measurements with a K-type plugged into the XDM1041, another K-type in the BM869S and a PT100 probe in the 3441A, all in close proximity, revealed this wonderful roller coaster-like graph. The yellow legs are exactly 10 minutes apart. On the right you see an extract of the recording from the SCPI interface of the XDM1041. After 372 seconds, the meter stops responding to the commands to report the measurement value. The command times out and is repeated the next seconds and so on. After 3 missed responses, the meter suddenly responds to the next command and also delivers the queued response to the 3 previous commands. This is then followed at second 377 with a too high value followed by normal values. This cycle repeats 600 seconds later at 978 and so on. Because my program treats the missing responses as 0, we end up with the legs of the roller coaster. My conclusion on what's happening here is that the XDM1041 updates its cold junction reference value every 10 minutes while the K-type temperature function is selected. While that happens and the processor calculates or looks up the equivalent millivolt values of the cold junction, the meter is too busy to answer the SCPI interface. After 3 seconds, it resumes normal operation. The temporary overshoot is probably a bug in the firmware. This test was done when the ambient temperature was between 27 and 28 degrees Celsius, which was during one of the recent heat waves we had in the UK this year. Although the vertical scale of the coaster graph covers a fairly wide temperature range, you can still see that at the higher temperatures, 40 to 60 degrees Celsius, the lines of the 3 sensors are practically on top of each other. But when using a Peltier element to dip below ambient to 15 degrees Celsius, the lines seem to be more apart. Since these tests are very time consuming, I decided to concentrate my tests to the below ambient range where the differences were significant. The left side is basically a repeat of the below ambient part of the previous test but with higher resolution. It is clear that the yellow trace, which is the XDM1041 temperature, is significantly lower than the other two, while the BM869 and the 34401 with the PT100 probe were relatively close to each other. The right side is yet another repeat of the test, but this time I swapped the K-type sensors between the BM869 and the XDM1041 without changing anything else. First of all, it may appear that some of the 10-minute marks are missing, but that is just because in each cycle the program was collecting data not just from the XDM1041 but also from the BM869 and the Agilent, and especially the Agilent takes some time to do a measurement if you set it to the highest resolution, so each cycle was slightly longer than 3 seconds. This means it's entirely possible to just miss the 3 seconds pause when the processor updates its cold junction reference. This is why the graph on the left have marks every 10 minutes and the other one on the right have some missing, even though exactly the same software was used to record both. If we compare the graph, it now appears that the yellow trace tracks the blue PT100 curve much closer at lower temperatures, but starts diverting more when the temperature gets closer to ambient. Besides the fact that K-type probes are actually rather inaccurate, even the branded one I bought with datasheet and all is only plus minus 1.5 degrees Celsius. A possibility is that the cold junction temperature of the XDM1041 is simply not correct. For example, if the cold junction is actually 1 degree hotter than what the XDM1041 thinks it will report a 1 degree too low temperature and vice versa. To find out, I recorded the cold junction temperature as reported by the XDM1041 over almost 5 hours. This is the yellow trace. The blue trace is the ambient temperature and the red trace is the temperature inside the black COM socket of the XDM1041, which I simply measured by shoving a temperature probe into it. You can see the staircase of the cold junction adjustment at the beginning of the yellow trace. Since the measurement interval was set to 10 seconds, most of the legs are missing. It is striking that the socket temperature is at least 1 degree higher than the cold junction temperature and almost 3 degrees higher than ambient. The warmer than ambient socket could explain why the XDM1041 measures too low with this type of K-type sensor. The cold junction is directly at the banana plug, so if they are plugged into a warm socket, they will eventually warm up too. The other K-type, which has better results at the XDM1041, uses the small plugs common to temperature sensors to allow usage with different types of probes. Here the cold junction is inside the small green plug, which is a fair bit away from the sockets of the XDM1041. This cold junction stays much closer to ambient. Overall, the K temperature measurement works reasonably well, but your accuracy is depending on the way the sensor connects to the meter. Also, you need to wait at least 30 minutes to let the meter refine its approximation of the cold junction temperature, and it's best to run the backlight at low intensity. With all the trouble of the K-type probes, you may want to use a PD100 with the XDM1041, which are anyway far more accurate. However, as I explained in the last video, it's problematic because the XDM1041 does not compensate for the wire resistance. In my PT100 probe, that wire resistance is 0.267 ohms. If you ignore the wire resistance, you get a 3% error at 20 degrees Celsius or room temperature. That error goes down as the temperature increases, so at 60 degrees or more, you don't have to worry about it anymore. This is of course only true for my probe. It may be different for yours. And speaking of your probe versus mine, you might well have a different XDM1041 too, because since I bought mine, OWON was busy to do some modifications. The newer models have a USB socket instead of the RS232DB9 socket. A fellow EVV blog member Dave BB has kindly provided a picture of the interface board in his newer XDM1041. However, all that OWON did here is integrate the chip that is in the usual serial to USB adapter cable into the meter. So communication is still using the same serial interface, and despite appearances, you don't get a true USB capability with a newer style meter. Next, you recall that my XDM1041 has firmware revision 1.2.0, but I had heard that newer models come with 1.3. I did not hold out much hope that the firmware in the XDM1041 can be upgraded, nor that OWON would respond to my request, but amazingly they did. I got a zip file that contained the new firmware binary, instructions, and 2 Windows installers, one for a serial driver and the second for a patch program. As you can see from the instructions, you connect the XDM1041 to the Windows PC, install the patch program, then run it, provide it with a COM port of the XDM1041 and point it to the firmware file. Then turn the XDM1041 off and on, and that should be it. Simple enough. Since my ancient Windows 7 had no problem in discovering the serial to USB chip used in my adapter cable, I did not need the driver, so the first thing was installing the patch program. I used an external second monitor for recording this on the laptop, and the windows kept popping up on the other one, so I had to drag them to be included into the recording. Anyway, there isn't really anything earth-shattering happening here, just a normal install, and I accelerated the video a bit to save time. Once it's running, you select the new firmware, which is a bin file, and the right COM port, which is 6 in my case. Initially the program refused to do anything, and it took a while before I realized that I had forgotten to tick the box next to OS. Once that was done, it started printing messages that it was trying to enter download. That was when I turned the XDM1041 off and on again. Normally the XDM1041 shows this yellow progress bar on the screen at boot up. In this case, the empty bar remained. Unfortunately, the camera lost focus, and I did not notice that for a while because I was looking at the Windows 7 screen. Anyway, we did not miss anything because nothing is happening on the XDM1041 screen during the download. Back on the Windows PC, it looks like the download tool is periodically announcing its presence to the XDM1041 with some special command, and during boot up, the XDM1041 goes into download mode if it detects that message. Once it sees that the XDM1041 is ready, the download tool starts pushing the new firmware in 12 chunks, 0 to 11, to the XDM1041 and then does some checking to confirm it got there okay. That's all, nothing else happens on the Windows machine. On the XDM1041, after the end of the download, the normal display simply appears, no special message or similar. You have to press the utility screen to find out if anything has changed. Indeed it has. The version has changed from 1.2.0 to 2021 0525, which is obviously a date, 25th of May 2021, and the checksum is different. To be honest, I have not found anything that is obviously different or changed. The user interface annoyances I mentioned in the last video are still there, and the auto ranging in capacitance mode is still not working properly for higher capacitances. I have asked OWON for some release notes, but they have not responded so far. I have also asked if I can pass the firmware on to other XDM1041 owners, again with no reply. Maybe it's time for a reminder, and I hope I get an answer for the next video on all things SCPI. So don't forget to subscribe if you have not already, and maybe consider becoming a Patreon, link in the description. As a Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.